Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Honours Physics students. Now we are going through optics, which is intended for the 4th semester students. The geometrical optics, that is the first section, and in the lecture 6. And so the contents of this lecture are first we will have a detailed study of the cardinal points, need for introducing cardinal points, the idea of introducing cardinal points, principal points and principal planes, focal points and focal planes, nodal points and nodal planes. The optical instruments have collection of image lenses, not a single lens. When you have got collection of lenses, then you have to make use of the idea of cardinal points. And it is in 1841, Gauss showed that any number of coaxial lenses, you have number of lenses, coaxial means passing through the optic axis, passing through all the lenses, number of coaxial lenses, then the coaxial lens system can be considered as a single lens, an effective lens, provided a single unit for which the lens maker's formula, which I will be showing again today, can be applied provided the distance are measured from 2 hypothetical parallel planes. What we have been doing in the last lectures with regard to optics, we had made some approximations when we were discussing about the Fermat's principle of least time and the equivalent focal length of a lens system. We always considered the paraxial rays. Now I am telling you the approximations which have been used so far in my previous lectures, or in general in optics, the approximations which are made are, you say sin alpha is equal to alpha or tan alpha equal to alpha. When can you make sin alpha equal to alpha or tan alpha equal to alpha? Only when, what is alpha? Alpha is the angle made by the light ray with respect to the lens. You have got a lens here, the angle made by subtended by the light ray on the surface of the lens, that the angle made is should be very small. Then only you can make sin alpha equal to alpha or tan alpha equal to alpha. By this, what I mean is, we are considering only the paraxial rays. What are paraxial rays? Light rays very close to the optic axis, or in other words, which do not make a very high angle if it subtends a large angle with respect to the surface of the convex lens. Those light rays, as you know, they are called the marginal light rays, because the lens is here, they lie at the margin, at the extreme end, the marginal light rays. Now I am considering only the rays which are almost parallel to and close to the optic axis, they are called the paraxial rays. And in the last lectures also I told you about the approximation that we are considering only the paraxial rays, light rays, so that I can make sin alpha equal alpha or tan alpha equal alpha. These approximations have been done. Second approximation is the formulae that we have obtained so far or derived so far are for generally thin lenses. By a thin lens, as all of you know by now, the lens thickness is so small, the center can be the distance separating the center and object, the center of the lens and the image, these distances can be made with respect to the surfaces. The lens is like this, the surface is here, you measure the distance between the surface and the object, so this surface and the image, and so the center is somewhere at the center of the lens, but because the lens is so thin, you are neglecting the thickness of the lens. You define a thin lens as one in which the thickness is very small, that is a thin lens, it can be ignored. Now, the two approximations which have been made so far in the lectures are, one is the paraxial approximation, then the other is the formulae that we have obtained are applicable for the case of thin lenses. But what about thick lenses, or instead of a thick lens or a set of lenses? For a set of lenses, as I will be discussing now, a coaxial lens system, you have got a objective, eyepiece and so on. For a set of lenses, the formula that we have obtained cannot be applied, and now we are considering a coaxial lens system, a set of lenses, and we want to find out how the cardinal point, the idea given by Gauss, the Gaussian points or the cardinal points, this concept which is given can be, they are hypothetical planes. I am going to introduce what are called the hypothetical planes, principal planes, nodal planes and so on, and now these ideas will simplify the problem. What is simplification? Suppose you have got objective here and you got the eyepiece here, you got objective, the object is looking here, the eyepiece is somewhere here, another lens is here, and now the light ray which is passing will undergo refraction here, that is air to glass, right, the one refraction, and then again from glass to air, second refraction, and then the eyepiece is here, again the third refraction, that is from surface to the glass, then from glass to the surface again. So, there will be 4 refracting surfaces which the light ray will encounter when it is trying to pass through a 2 lens system. You have got objective and eyepiece. When you have got 2 lenses, as we will be showing now, then the light ray will undergo refraction due to 4 different surfaces. Now, by using the cardinal point principle, these refractions, successive refractions suffered by light ray at 4 different points can be ignored or can be replaced by using the what are called the principal planes and nodal planes. So, there will be the cardinal points. There are 6 points which you call as the cardinal points, 2 focal points, the first principal focus and the second principal focus, which I will be showing later, or I have told you partly in the first lecture. There are 2 focal points and 2 principal points and 2 nodal points. These 6 points are referred to as the cardinal points, or because they were introduced by Gauss, they are called the Gaussian points. So, let us now look at again the optical system. It consists of more than one lens. Gauss showed that a combination of lenses, as I told you, can be considered as a single lens having an effective focal length. The incident ray, which I am showing in the next diagram, you have got an incident ray here, OA, okay. This is incident ray OA, which is incident on the lens, undergoes refraction at 4 spherical surfaces and follows the path OABF2. I will go to the 2 lenses are there. As I told you just now, when a ray of light tries to pass through a 2 lens system, you got 2 lenses, maybe objective and eyepiece, then what happens? It comes across 4 refracting surfaces. Now, what are the 4 refracting surfaces? The light comes here, it is incident at the point A, it undergoes refraction through the material of the lens, which obviously be having a different refractive index compared to air here. You got air here, you got a material here, right. This is the first refracting surface. Then light ray passes here, then it comes across from glass to air. Here air to glass, that is one refracting surface. Then from glass it emerges to air, the second refracting surface. It follows OA, then B. Up to the point B, the third refracting surface, right. Then again from glass it emerges here, this is the emergent ray BF2. So, from glass again it comes to air. So, one refracting surface, the second one, third one and fourth one. So, a light ray or any light ray which goes through a two lens system will undergo refraction at 4 different curved surfaces. Now, this can be, this particular 4 refracting surfaces, whatever that deviation suffered by light ray, can be simplified by using the planes which I am talking about, the 2 principal planes and 2 nodal planes. I will be talking about principal planes and nodal planes, and using these planes, these difficult deviations differed by light ray at 4 different refracting surfaces can be simplified. And now look at the light ray OA here, which is incident on this surface. It undergoes it takes a route OA BF2, right, OA BF2, and you have it undergoes a deviation delta 1. Delta 1 is the angle by which the light ray has been deviated. If the medium would not have been there, the light ray would have gone in this direction, OAH2. It would have gone OAH2T, right. Now, it has undergone a deviation through an angle delta 1. So, the incident ray OA is extended now forward in the same way as the emergent ray BF2 backward, they will meet at H2. What I mean is, you introduce this kind of OA is here, you direct it, you draw the line as if suppose the medium would not have been there, then the light ray would have gone along the direction OAH2. So, right, OAH2 is here, this is the direction. Now, because it is undergoing deviation, it goes to F2. Now, this F2 can be from the B, from the point B, you draw a line say in this direction. So, you have got B here, B to actually the light ray undergoes deviation delta here, right, deviation suffered by light ray. So, you make the light ray to go, assume it is going along this direction AH2. When will it go along AH2? If the second medium would not have been there, it would have gone in this direction, right. Then you make the light ray from B to, you project the light ray, you make the light ray to go in this direction, then this delta 1 will be having, you will be having here BF2 backward. This is BF2 is here, you make BF2 to go in this direction. If the light ray goes in this direction, so BF2 is the light ray, the direction in which light ray is travelling. Ultimately, you direct it, you make it to go in this, you draw a line which cuts OAT. OAT is the line drawn. What is OAT? The incident ray would have gone in this direction, that is OAT. You make this BF2 to cut, you extend BF2, then it will be meeting at this point here H2, the angular deviation delta will be here. So, this H2 P2 will be called the principal plane. So, effectively instead of this delta 1 and delta 2 being considered, the 2 deviations delta 1 deviation because of first lens, second deviation delta 2 suffered because of the second lens. This can be effectively considered as if you have a lens or you have got a plane which makes an angle delta, so that the light ray comes to F2 finally. So, the point I want to emphasize is, if the incident ray OA is extended forward, the same way the emergent ray BF2 is directed backward, they will meet at H2. That is the point I showed you just now. Now, we can consider the entire refraction in terms of a single refraction taking place at H2. That is what I told you, a single refraction taking place at H2, that is the effective thing, that is the so called the principal plane. Instead of 2 lenses, you can consider a single plane. We will have a break at this point, then we will discuss the rest in the after break. Welcome back to the break. Now, what I am trying to repeat and make you to understand is the following. The light ray is traveling through two lenses. From OA it comes to BF2. Now, what I am trying to do is instead of the deviation suffered by the first lens, light ray by the first lens, and the deviation suffered by the light ray due to the second lens, that the entire thing I am replacing by the deviation delta suffered by the light ray at this point. Assume that you have got something here which is able to make a deviation delta, so that the light ray comes here, comes to the point and undergoes a deviation delta. From if it undergoes a deviation delta, it will come to F2, right? Instead of the first deviation delta 1 suffered by light ray at the first lens, the second deviation delta 2 due to the refraction produced by the second lens, I replace these two deviations by a single deviation, right? Delta, is that right? Single deviation that the light ray will experience because of the plane H2 P2. H2 P2 is the plane, P2 is the principal point, H2 P2 is called the principal plane. So, the same effect that is produced by two lenses can be replaced by a deviation produced by a single deviation produced at the point H2, right. That is what I am trying to tell you now. Consider the plane passing through H2 and the perpendicular to the principal axis, and this plane is the so called principal plane of the optical system. The entire optical system I have now a principal plane. The four deviations caused by the four refracting surfaces is made equivalent to a single refraction taking place at H2. I will go back to the picture again, and you have the four refractions. What are the four refractions? As I told you, you have got one refraction here, another refraction here, that causes the deviation delta 1, the third one refraction here, fourth refraction taking place here. All the four refractions can be replaced by a single refraction which is experienced by the light ray at a point H2, because the emergent ray is found at the same point F2 as produced by the two single lenses. So, the two single lenses can be replaced by a plane which makes it is a hypothetical plane. It is only a conceptual plane. It is not the actual. It is a conceptual plane, or you know, it is a hypothetical plane which makes an angle of deviation delta, so that the light ray comes to the focal point F2. Is that right? So, that is what, instead of the four refracting surfaces giving rise to a deviation, effective deviation, and the light ray coming to F2, that can be replaced by, or it is equivalent to a single refraction taking place at the point H2, which I showed you here. And H2 P2 is the so called principal plane in the image space. It is called a second principal point. It is called closer to the image, it is called a second principal point, whereas the first principal point will be somewhere here. I will show in the pictures to come where you will be having the first principal point. As you know, in optics there will be two principal points, two principal focal lengths. In the case of thin lens, F1 and F2, the two principal focal lengths can be equated to one another, it will be equal to one another in the case of a thin lens. So, it is called a second principal point nearer to the image, it is called image space. So, now look at the principal points and principal planes. If you have got a light ray here, a beam of light coming from the point F1, what is F1? F1 will be called the first principal focal point. F1 will be called the first principal focal point, that is taking place in the object place, whereas this is called the image space. Now, this is the object space. So, you have got the object here, and you have got F1 is a point from which the light ray comes. It is incident on the first lens. It makes a angle of deviation delta 1 here, and then you have got delta 2. You have got a delta 2. So, the light coming from F1 suffers deviation. The light ray should have gone in this direction, right. As in the earlier case, what I do is I assume the light ray to go undeviated like this. If the lens would not have been there, then the light ray would have gone from F1 to H1. Is that right? F1 to H1. Okay. Then because you have got the light ray here, so what I do is I make the light ray to go, assume the light ray to go undeviated, and then what I do is I make a line like this TH1 parallel to the optic axis, parallel to the optic axis, right, passing the center of the lens. The H1 is TH1 is here. This I will be calling as the first principal plane, is the first principal focus, first principal focal point, and so you have got the delta 1 deviation suffered at the first lens, delta 2 the deviation of the light ray produced by the second lens, and this will be your delta. So, the deviations caused by the two lenses, as in the earlier case, can be effectively replaced or reproduced by a single deviation delta that will be experienced by the light ray due to a plane H1 P1. So, we are adopting a similar procedure as we did earlier, as shown in the figure B. For the refracted ray at L1, draw a line. You see the refracted ray, you draw a line parallel to the principal axis, which is TQ. TQ will be the line drawn parallel to TQ is here, line drawn parallel to the optic axis, right. So, line drawn parallel to the principal axis, which is TQ. TQ means F1 H1 at H1, right. TQ will be meeting the, suppose the light ray would have gone in this direction, then the light ray would have met your TQ at a point H1, and so H1 P1 is the second principal plane, H1 P1 is the principal plane, and P1 is the principal point in the object space. I told you the principal point on the image space earlier. Now, this is the principal point in the object space. This is the principal point F1 in the object space. We will now pass through the principal points and principal planes in the case of a two lens system again. So, you got now we had only earlier cases, we had the first principal focal point and the second principal focal point. This is the second principal focal point. Okay, you had two focal points. Now, let us consider the two lens system again. We have F1 here, the light ray coming along this direction, and you have got another light ray coming along OA. So, two incident rays are directed towards H1, right. The two light rays coming from the 2 points along this direction OA and along this from the point F1, the two light rays which are coming here can be seen to come from H2 after refraction. H2 is the image of H1. Thus, H1 and H2 are called the conjugate points, okay, and H2 P2 are the conjugate planes. So, these two principal planes are called the conjugate planes. H1 P1 and H2 P2 are called the conjugate planes, and also H2 P2 obviously the heights H2 P2 and H1 P1, the heights H1 they will be equal to one another. H1 P1 and H2 P2 will be equal to one another. Hence, the lateral magnification is unity. The magnification is unity. The principal planes have unit magnification and are called unit planes, and P1 and P2 can be called as unit points. P1 and P2 can be called as the unit points, and they are the unit planes because the the magnification is unity. These planes or points are hypothetical planes and points, and were introduced by Gauss to simplify the problem. What is simplification? The simplification is, instead of looking at the 4 refracting surfaces, we will be talking about the refraction suffered by light ray because of the 2 principal planes. The 4 refracting surfaces are replaced by 2 principal planes. So, I mentioned about the first focal point, the second focal point. F2 is called the second focal point of the optical system, as you know by now, that is the focal point, the image obtained at the image space, where F1 is the image obtained at the object space. So, definitely the focal point, first focal point on the principal axis for which light passing through it becomes parallel to the principal axis after refraction, and the other one is called the first focal point. Okay. The second focal point is a point on the principal axis for which a beam of light travelling parallel to the principal axis after refraction passes through it. Planes passing through the principal focus f1 and f2 are perpendicular to the axis and are called first and second focal planes. You have in lenses two principal focal lengths, f1 you got here, f1 here, f2 here, and in general in the case of thin lenses f1 will be equal to f2. The nodal points are points unlike the principal planes replace the refractions suffered by the four refracting surfaces. In the four refracting surfaces you end up with two planes, two hypothetical planes, two principal planes. Now refraction will be occurring at the two principal planes, whereas the nodal planes will not give rise to any refraction. The difference between the principal plane and the nodal planes are the principal planes will lead to deviation, or they are the hypothetical planes which will give the same amount of deviation as that of the two lenses. Whatever deviation that will be suffered by the light ray, because the two lenses will be equivalent to the same deviation that is produced by the principal planes. So, the principal planes will refract the light rays, whereas the nodal planes do not involve in the refraction. They will not be refracting in the light ray. Nodal points are points on the principal axis where light rays without refraction, this is very important, without refraction intersect the optic axis. In a thin lens, the nodal point is the center of the lens. In a thin lens, the nodal point refers to the center of the lens. We will now go to the summary part of this lecture. The image of an optical system can be easily obtained using the concept of cardinal points. Principal planes refract the light rays, whereas nodal planes do not refract light. They are the hypothetical planes. The above planes are hypothetical planes which are introduced basically to simplify the problem, wherein instead of four refracting surfaces giving rise to deviation light ray, to simplify the problem we have done the cardinal planes and the Gaussian points. The questions which we have are: what are Gauss points? What is the difference between the principal plane and the nodal plane? The last question being, what is the advantage of using the idea of cardinal points and above mentioned planes? With this we come to the end of the cardinal points. Now the cardinal points will again be taken up to obtain the image of an object. That will be discussed in my next lecture. Thank you.